Hey everyone, welcome back for another deep dive.
Mhm.
Today we're going to try to, wrap our heads around impedance and resonance in AC circuits.
Oh, yeah.
Those concepts that always seem really complex, but they're like actually everywhere in the tech we use all the time.
Yeah, it's like the hidden language of, radios and Wi-Fi and all that stuff.
Exactly. So to kind of set the stage, maybe we should start with just a quick comparison of AC and DC circuits, like, level set a little bit.
Right.
In a DC circuit, things are pretty simple. It's like a steady flow, like a calm river. Voltage and current are constant.
Yeah, but then when you go to AC circuits, it's like that river suddenly turns into like rapids.
Yeah.
Voltage and current are constantly changing direction, going back and forth. And that's where this whole impedance and resonance thing comes in.
Okay, so that constant change in AC is where things get a little funky. But before we even get into impedance, let's talk about the components that make AC circuits unique capacitors and inductors.
Right.
How are these guys different from just your normal everyday resistor?
Well, a resistor is kind of like a rock in the river, right? It slows the current down consistently no matter what. But capacitors and inductors, they're a little bit more dynamic. They can actually store energy. And that causes a kind of time delay, like a phase shift between the voltage and the current.
So it's like the voltage is trying to lead the current in a dance, but the capacitor or inductor is like, hold on a sec.
Yeah.
I need to gather some energy before I can follow your lead.
That's a great analogy. And that whole dance between the voltage and the current and the energy storage, that's where impedance comes into play. It's like the total opposition that an AC circuit puts up to the current flow. It includes the resistance, but also this new thing called reactance.
Reactance being the pushback from those energetic capacitors and inductors.
Exactly. And we represent that impedance with the letter Z, and there's a formula for it. It takes into account the resistance R and the reactance X. So Z equals the square root of R squared plus X squared.
All right, starting to see how this all fits together, but how does the impedance change when we connect these components in different ways, like series versus parallel?
Ah, good question. That's where things get a little trickier. The formulas for calculating impedance, they actually change depending on how you arrange the components in a series circuit.
Yeah.
You basically add the resistance and reactance directly, but you got to be careful about whether the reactance is coming from a capacitor or an inductor. They actually have opposite effects.
So it's almost like we're dealing with different types of resistance. Some are positive and some are negative, and we have to kind of balance them out.
Exactly. And when you have components in parallel, the calculation gets even more funky. You're essentially looking at how much each pathway contributes to the overall flow and then combining those contributions.
Okay, I see why people get tripped up by this. We've got these formulas, but
Yeah.
is there a more visual way to understand how these different resistances and reactances are all playing together?
Absolutely. That's where those vector diagrams come in really handy. You can think of it like a right triangle where the base of the triangle represents resistance, the vertical side is the reactance, and then the hypotenuse of the triangle represents the total impedance, and the angle between the resistance line and the impedance line that gives you the phase difference between the voltage and the current.
Ah, so we're not just looking at numbers, we're actually looking at directions too. So the longer the hypotenuse, the greater the impedance, and the bigger that angle, the greater the phase difference.
You got it. Those vector diagrams are super useful for visualizing how everything's related.
This is starting to make a lot more sense now. I think we've laid a really good foundation, wouldn't you say?
Definitely. I think we're ready to dive into the really cool stuff. Resonance. This is where things get really interesting.
All right, let's do it. I'm ready.
Okay.
Okay, resonance. This is the part I've been kind of excited about. It sounds almost like something out of like a sci-fi movie,
Right.
what's actually happening when a circuit resonates.
Well, those capacitors and inductors we were talking about, it's kind of like they're kids on a seesaw. They're always exchanging energy back and forth. Resonance happens when they hit that sweet spot where their energy exchange is perfectly in sync.
If they're not working against each other, they're like working together.
Exactly. And at that point of perfect harmony, something really cool happens to the impedance. Remember that right triangle we were talking about?
Yeah.
At resonance, that triangle basically collapses because the reactance from the capacitor and inductor, they cancel each other out.
Wait, so the impedance just drops to like its minimum. It's like all resistant.
Yeah, it's like the circuit suddenly finds this clear path and the current at that specific resonant frequency can just flow through easily.
Wow, that's pretty wild. But why do we care about this resonance thing? Where does this show up in real life?
Resonance is everywhere. Think about like tuning an old school radio. What you're doing is actually adjusting the capacitance to change the circuit's resonant frequency, and you're trying to match it to the frequency of your favorite radio station.
So it's like finding the perfect match between the radio circuit and like the incoming radio waves.
Exactly. And it's not just radios. Resonance is behind so many different technologies. Have you ever heard of MRI machines?
Uh-huh.
They use resonance to create those detailed images of the inside of our bodies.
No way. So this seemingly simple concept is like powering some of the most advanced tech we have.
Absolutely. And it's also crucial for filtering out unwanted frequencies. Think about audio equipment filters. Use resonance to separate the high notes from the low notes and give you that nice, clear sound.
Okay, my mind is officially blown. So we've got these circuits resonating, impedance dropping, currents flowing. But what happens when we deal with parallel circuits? Does resonance still work the same way?
That is a great question. And this is where things get a little counterintuitive in a parallel resonant circuit. The impedance actually reaches its maximum at resonance.
So what I thought parallel connections were supposed to like decrease impedance, like adding more lanes to a highway.
You would think so, right? But in a parallel resonant circuit, something unique happens. The capacitor and inductor, they form what we call a tank circuit, where energy just oscillates back and forth between them.
So it's like a closed loop of energy just bouncing around.
Exactly. And because that circulating current isn't flowing out to the rest of the circuit, the overall impedance appears really high. It's like a hidden reservoir of energy.
That's so interesting. So it's not that the impedance of the individual components is increasing. It's more like the tank circuit is kind of hiding a bunch of the current, making the overall impedance seem higher.
Exactly. It's a subtle but important distinction. And this high impedance at resonance is actually super useful in applications like oscillators, which are the heart of so many electronic devices.
Wow. I never thought I'd find impedance in resonance. This is fascinating. We've covered so much ground. But I'm curious, is there anything else about resonance that's particularly intriguing?
Well, one thing that always gets me is how we can actually manipulate resonance to our advantage. We can design circuits with specific resonant frequencies to target certain applications like wireless communication or medical devices.
It's almost like we're conducting an orchestra of electrons,
Yeah.
getting them to dance to our tune.
That's a great analogy, and this ability to control resonance is what makes it such a powerful tool in electronics. It lets us really harness the power of AC circuits to create some amazing things.
This has been such a cool journey into the world of impedance and resonance, from those dancing currents in AC circuits to the clever tricks for optimizing power usage. I feel like I've gained a whole new appreciation for how complex and intricate the world of electricity really is.
And that's what's so cool about electronics. There's always something more to learn, something more to explore, and always new ways to push the boundaries of what's possible.
Absolutely. A huge thanks to our expert guest for breaking down this complex topic with such clarity and passion. And to our listeners, thanks for tuning in and diving deep with us. We hope this episode has sparked your curiosity and empowered you to explore the endless wonders of electronics. Until next time, keep those circuits buzzing. Okay, so let's talk power. The thing that makes all of our circuits actually, do stuff in DC circuits. It's pretty simple, right? Voltage times current equals power, but I have a feeling things get a little more interesting in AC.
You could say that with AC power, it's not just about like the raw amount of power flowing, but also like how effectively it's being used. And that's where this idea of power factor comes in.
Power factor, is that like a measure of how much of the power is actually doing something useful?
Exactly. Think of it like ordering a giant pizza. You've got all those slices of parent power, but you can only realistically eat like half of them. That's the true power. The power factor tells you like what percentage of the pizza you're actually consuming.
Okay, I like that analogy. So a power factor of 1 means we're like, crushing the whole pizza, using all the power efficiently. What causes the power factor to drop below 1 in AC circuits?
Those reactive components we were talking about before, the capacitors and inductors, they tend to like hoard some of the power. They store it temporarily in their electric and magnetic fields. And this stored power, we call it reactive power. It doesn't actually do any useful work.
So reactive power is like the pizza crusts, technically part of the pizza, but not really what we're there for. But why is this a big deal? Like, why do we care about a low power factor?
Well, imagine ordering that giant pizza, eating only half, and then still having to pay full price. That's what happens when your power factor is low. You're drawing more power from the source than you're actually using, and that leads to wasted energy and higher electricity bills.
That makes sense. So a low power factor is like paying extra for those pizza crusts. Nobody wants it. What can we do to bump that power factor back up and make sure we're getting our money's worth?
Well, one really clever trick is to use capacitors for power factor correction. Remember how capacitors like to store energy?
Yeah.
Well, they actually do it in a way that kind of cancels out the energy storage of inductors.
So it's like adding a side salad to our pizza order.
Yeah,
Something light and refreshing to balance out those heavy, cheesy slices.
exactly. By carefully choosing the right size capacitor, you can offset that reactive power from the inductors and bring that power factor closer to 1, making the whole system more efficient.
That's really cool. So by understanding these like subtleties of AC power and using techniques like power factor correction, we can actually optimize our electrical systems to be way more efficient.
Absolutely. And this is just like scratching the surface of what we can do with AC circuits. By mastering these fundamental concepts of impedance and resonance and power, we can really unlock the potential to design and build some truly innovative technologies.
Well, this deep dive has been an absolutely electrifying journey from the dancing currents in AC circuits to those clever tricks for optimizing power usage. I feel like I've gained a whole new appreciation for like how complex and intricate the electrical world really is.
And that's what's so exciting about electronics. There's always more to learn, more to explore, and more ways to push the boundaries of what's possible.
Absolutely. A huge thanks to our expert guest for shedding light on this complex topic with so much clarity and passion. And to our listeners, thanks for tuning in and diving deep with us. We hope this episode has sparked your curiosity and given you a new appreciation for the incredible world of electronics. Until next time, keep those circuits buzzing.